Okay, today we're going to look at proton NMR. So we're going to see some differences between the actual look of proton NMR versus carbon NMR. And we're going to delve deeper into understanding why that is. And really it relates back to the isotopes of carbon and proton for hydrogen. So we'll go through the chemical shift argument first, based on electronegativity. As we start substituting groups from methane, now we're going to look at how does that affect the hydrogen shift. So the same principles apply, but the spectrum has a shorter window. And then we'll look at why proton NMR signals look the way they do. So there's an empirical rule that we can develop, and then that's going to help us ultimately figure out connectivity. So remember, IR is giving us the presence or absence of functional groups. And those are discrete, sort of smaller collections of elements and bonding patterns. So that's some connectivity. Proton will give us a little bit more of the picture there, and through that we'll develop an intuition about how to assign every carbon with attached hydrogens from a spectrum. Any questions before we get started? So sort of circling back about terminology. And so we talked about the Greek letter delta. So delta being the chemical shift, and that's reported in parts per million. So the spectrum line width you see there is for proton, and notice it runs from 0 on the right to about 12 on the left. So contrast that to carbon NMR, which was 0 to about 220. So essentially what we're doing now, when we're looking at the hydrogens, all of those functional groups are compressed to about 12 parts per million. In carbon, it was 220. So an issue that arises with proton NMR is that you can have these signals overlapping one another. And that can lead to some complications in interpreting what those signals are. So the way that the instruments operate is it's basically a giant magnet. And so that magnetic field is fixed. We'll talk a little bit more about that probably on Wednesday. The magnetic field is fixed, and within that field, you're going to get your spin alignments. Remember, we said there can be spin clockwise or spin counterclockwise, or sometimes it's called spin up or spin down. And they're all randomly pointing in different ways in that field. The other component to the NMR experiment is the operating frequency. And on this table to the top left, you can see the different frequencies. So 60, 90, 400, 500, 600, there's 800 and now also 1.2 gigahertz. So the ones you see there are listed in megahertz. And the way that relates to the chemical shift is that for every 1 part per million, that's how many hertz you have. So this number here in the second column, we can think of as resolution. And on the top right, you see the 1 part per million. And the higher the operating frequency, the more resolution. And that's like, this TV screen up here, things are like 4K. Back when I was young, televisions were like a cathode ray tube. and the resolution kind of sucks. You might even say like potato cam, if you know what that is, very pixelated. But the more resolution you have, the finer those signals will look. So going up from 60 hertz to 600 hertz, it's a tenfold increase in resolution. What that means is if you have peaks that overlap at 60 hertz, at 600 hertz, they'll appear separated. So the greater the operating frequency, the greater the resolution. And the chemical shift is defined as the distance downfield. So what does that mean? In TMS, so TMS is this compound, tetramethylsilane. And that's added as a calibration that's set to 0. So the distance downfield divided by the operating frequency of the spectrometer. So hertz divided by megahertz, that gets you parts per million. And I have this terminology here. Towards 0 is called upfield. That relates to the magnetic field strength. So upfield towards 0, downfield towards 12. And you have this magnetic field. Another way of describing it, when they're closer to 0, they're called shielded. When they're closer to 12, they're called deshielded. And then the last term, frequency, relates to the energy of the radio wave required to flip the spin. So when we're talking about chemical shift of similar things, people commonly say upfield. This is more upfield or this is more downfield. And so you really just have to know the direction. So here are the proton NMR spectra of our ester. And ketone, again, we were going through that exercise. We had this molecular formula, we had this IR, and we came to these two possibilities. And we said for that, the ester, there would be 3 unique carbons, 2 sets of proton that integrate to 2 and 2. So if this is the proton NMR, what you're seeing now is you're seeing a signal, that's one set. You're seeing a second signal, that's the second set. Because these two numbers are equal, 2 and 2, I'm going to write this below, 2 and 2. So in this exercise, we call that a ratio, but on the actual spectrum, we call it integration. So it's conceptually the same thing. For the ketone, we had 4 unique carbons, 3 unique sets in a ratio of 3 to 3 to 2. So here you see your sets, 1, 2, and 3. But now the ambiguity, see this 3, 3, and 2? Like, what do we assign to what? And what we're going to learn today is sort of an indirect method of making that assignment. So under here, I'll just put, I'm putting a question mark because, again, those numbers are not equal. So we can't assign them just yet. And this is a blow up because the prior slide was showing you 0 to 10 or 0 to 12. And now what I've done is just blown up the regions so you can actually see what the signals look like. So notice that it's not just a line that goes up and down, but each signal has more lines now. And so for the ester, when we're looking at you take my glasses off here. I'm just going to say approximately 2 ppm. It's really tiny. And we'll say approximately 4 ppm. We'll just use these colors to make assignments. So the peak at signal at 2 ppm should belong to the blue dot or the green dot. So, it's the blue. So remember the logic that we were using for this. Now we're looking at hydrogen, but the logic still stays the same. As you substitute off from methane, you add carbons or heteroatoms, it's moving it more to the left. So the green dot has a carbon with an oxygen bonded to it. So the electronegativity is affecting that chemical shift more. So we can make assignments based on that, but when you look at these signals, so this signal at 2, how many lines in that signal do you see? 3 lines. And then the same for the green. So let's go to the ketone and then see if we can make some sense of why these signals look different with these line numbers. So let me write some numbers down here. I'm going to say approximately 1 ppm, approximately 2 ppm, 2.4 ppm. So I guess let's do it sort of the opposite way. The signal at 1 ppm, what color dot should that be? So yellow. 2 ppm. What? Blue. And then the last one is the green dot. So again, the logic is we're looking at each one, seeing how many substitutions we've done and how those substitutions will push it to the left past 0. So the yellow dot we can see has 3 lines. The blue dot has 1 line. And the green dot has 4 lines. If we go back up to the ester, remember I said the ratio was 2 to 2? So I'm going to just say under here 2 H's. 2 H's. So based on the electronegativity argument, we've made assignments for the ketone, blue, green, and yellow. So the yellow signal has 3 hydrogens. The blue signal also has 3 hydrogens. and the green has 2 hydrogens. Do you see some inconsistencies between the ester and the ketone? So the ester has a signal with 2 hydrogens, but 3 lines. Now in the ketone, you have this signal of 2 hydrogens, but that has 4 lines. And then the blue and yellow, they both have 3 hydrogens, but there's different number of lines. So how can that be? Yep.
It's the neighboring hydrogens plus 1.
So you're looking at the number of neighboring hydrogens, and you're adding 1. So that's called the N+1 rule. So lines determined by N+1 rule. So number of neighboring hydrogens. So that's an empirical observation. Again, on Wednesday or next Monday when we get to it, we'll explain why is it +1. What is the reason for that rule? But now we're just sort of looking at things and then predicting. So let's start up with the ester. See the blue dot? It has 2 neighbors, the carbonyl and then this. The carbonyl has 0 hydrogens. The green dot has 2 hydrogens. So 2 plus 1 is 3. You can do the same thing for the green dot then. The oxygen has no hydrogens. This blue carbon has 2, so 2 plus 1 is 3. That's why you get 3 lines. So if you think of it the other way, whenever you see a signal with 3 lines, it's telling you the number of neighbors is 2 hydrogens. So the ketone, see the blue carbon? There's only one neighbor. That neighbor has 0 hydrogens. So 0 plus 1 is 1 line. The green dot has 2 neighbors. The one to the left is carbonyl, that's no hydrogens. The one to the right is a methyl group, that's 3. 3 plus 1 is 4. So 1, 2, 3, 4. That's 4 lines. And then the yellow signal just has 1 neighbor with 2 hydrogens. So that gets you 3 lines. So using that, we're able to then assign or help confirm or add confidence to these assignments. Any questions? Yep.
So is that pretty much how you knew that the green and blue dots wouldn't like be swapped places?
Yeah, so that it's 2 things. It's the electronegativity. So see the green dot? If we sort of start with methane, so CH4, we've done a substitution. So this would then be our sort of yellow dot right here. And then we've done another substitution. So that carbon has 2 substitutions. So it needs to push it even further to the left than the blue carbon, which only has 1 substitution. But then you can also use this N+1 rule to add confidence to that. Any questions? So again, since we're looking at proton NMR now, so we're looking at the H signal, but the chemical shift is really determined by what is bonded to the carbon that's bearing that hydrogen, or that set of hydrogens, so this X group. In the proton NMR, if we set methane, so we're now looking at, pardon the bolded carbons, but we're looking at the hydrogens now. So I'll just put a star by those hydrogens. So in methane, if we say the chemical shift of that CH4 is at 0.23 ppm, we take that H, we substitute it for a CH3 group. That then shifts those starred hydrogens to 0.86. And then this is just the difference, 0.86 minus 0.23. So for every carbon that you add, you're moving it a little bit more than a ppm to the left. And then you can see the trend. So increasing electronegativity, you get these bigger jumps. And so also what that's telling you is when you start seeing signals in those regions, there's most likely a heteroatom attached to the carbon. And then the third column is, again, just the difference from methane. The halogen shifts, as we see here, when you start substituting the different halogens. Notice that it maximizes sort of at fluorine, and then as you go down the group, it starts moving back towards zero. And that's due to the electronegativity decreasing, but also the size of that heteroatom increasing. So even though we're in 0 to 12 in terms of the total spectral window, the region you see these is giving you an indication of what type of functional group is present. And again, there it is to point it out. The chemical shift at about 4. You've put that heteroatom on there, so that's going to shift it quite a bit. And then you have that carbon. So we're in that about 4.2 region. For the green, you have carbon, and you have sp3 carbon and sp2 carbon. So now you're at about 2.9 or something. One thing I do want to point out is there's not hard like endpoints to these things. These functional group regions will overlap. So, you don't want to memorize, 0 to 2.5 is only this. Because there is, sort of like a amorphous or error bar to these things. So we want the blue to be this. So we've done 2 substitutions. We'll take the green to be this one. And the other thing to point out is these 2 are relatively close to one another. And that is because they are connected by that carbonyl. So that's a piece of logic. We can say that they should be in the same chemical shift region. And then the yellow is most like methane. We've just substituted an H for a CH2. And again, when you look at that, it's like 1.05. I think when we did the math on the prior slide, we said a substituting a carbon should only be about 0.6. So, it's greater than 1, but what happens is, you've done that substitution, but all of this stuff along the chain, it's like tug of war. It pulls it a little bit more. So these are called additivity rules, and it's just based on empirical observation where the average chemical shift change is about this much. So let me do some changes of this. So this slide has both the carbon and the proton. So let me just make that clear. So it's a summary of both of those tables. Here's your carbon chemical shift difference, then your proton. So we were 220 to 0 ppm, and then 12 to 0 ppm here. But ultimately, if I use some dots here and say that carbon is looking at the carbon shift, so the blue dot, the green dot, proton, is looking at the proton shift. But really, all of that is influenced by what that X group is. And again, the trend of that really, the best explanation for it is, look at the electronegativity of what X is. Any questions? So on this slide, what we're going to look at is methane to the furthest right column. And then we're going to start sequentially substituting halogens. Notice the first structure on the left, we still have an H there. So we can't do 4 substitutions because it would no longer have a proton on it. So we're going to look at the halogens, and remember that electronegativity decreases that way. So our standard is methane. We're saying its chemical shift is 0.23. And so we're going to take H and substitute one of those for a halogen, either F, Cl, Br, or I. And then notice the chemical shift difference. Fluorine's the most. So you get a pretty big jump. So about 4 ppm. Again, iodine's the least because it's the least electronegative. And now this is the trap you don't want to fall into is when you add that second halogen, so now we have X and X. Notice in this column here for CH2X2, those numbers are not 2 times what we saw with just one substitution. Because otherwise that chemical shift now should be like what, 8.4 or something. So the more you add on there, it's not a linear progression. It's dying off a little bit each time. And then we do the third substitution. So we have CHX3, and notice it's not that big a jump to do the third substitution at this point. Does everyone follow that trend? So that was substituting on one carbon and then seeing the effect of the chemical shift of proton. So in a way, if we count the bonds, so from this X group, that's one bond, so X to carbon, and then those three H's are all equivalent. And so it's the effect through two bonds. But what if we have longer chains? What's the effect then? So for this, we're going to look at a 4-carbon chain. So this is a butane derivative. And at the 1 position now is our X group, so element X. And then what you see in the columns here, so carbon 1, carbon 2, carbon 3, and carbon 4, you're seeing the chemical shifts of the hydrogens attached to those carbons. So let me draw an H here. So again, that's 1, 2. So if that was fluorine, that would be at 4.49. Now the hydrogen on carbon 2, it's 1, 2, 3. So that's at 1.52. The H here, 1, 2, 3. That's 4 bonds away. That's at 1.34. And now the hydrogens on carbon 4, we have 1, 2, 3, 4, 5 bonds away. This is 0.95. So what this is telling you, the further you get away from that heteroatom, the more it resembles methane. Or stated another way, it like in tug of war, the person at the end of the rope is not really feeling all of the force that's being tugged on the rope. So again, I've just shown this for the halogen series, but the same thing would apply for other heteroatoms at that X position. So if you had an alcohol or an amine, or what other functional group present, the influence of that heteroatom decreases as you move away from it. Questions? So we've answered this a couple times. We'll just go through it again. We're looking at the CH2 group for A. We've done a carbonyl and a methylene substitution. So carbon versus carbon, that should look the most like methane, so it should be closer to 0. So B would be the correct answer. For carbon, the hydrogens on carbon B, you've substituted an oxygen. So that's going to really push it, past 3. Then you've done this other substitution of a CH2 group. So that's going to get you to 4.18.
So if we're kind of like doing this in the way that was done on the last slide, we would be going from the carbon, the oxygen on the far right, like the one with only single bonds?
Yeah, so this would be your like X atom. So if I draw a hydrogen from that B, you can see there's one bond, then two. And then to A, so 1, 2, 3. So the effect of that oxygen on the A hydrogens is much less. So again, for the ketone, the logic is that, B and C are both bonded to the carbonyl, so they need to be in about the same region. And then A is the most like methane, so that needs to be closer to 0. And so this should be 1.05. Using that, we can eliminate C and D. Now between hydrogens on B and C, C most looks like methane, so that's 2.10, and then B would be 2.39. So we would end up with A is the correct answer for that one. Questions? So here's our ketone with a stacked plot of the carbon signals on the top and the hydrogen signals on the bottom. So as we see, the carbon signals are just a line, but the hydrogen signals can have multiple lines. So 4 lines, 1 line, 3 lines. So what is the reason for that? So again, it has to deal with isotopes, and we saw in mass spec these different elements can have isotopes where the number of neutrons changes. And so in the table here, again, we see the atomic number. So carbon is 6, hydrogen's 1. And then it says NMR active nuclei. Notice the number for each of them. C13, H1. And that number must be odd. For the purposes of this class, when that's an odd number, the nucleus then has that spin up or spin down. The reason that the carbon looks different is due to this abundance here. The abundance of the NMR active nuclei C13 is about 1.1%, whereas in proton it's 99. So again, to be NMR active, you have this odd number for the number of neutrons. That implies there's this spin. Then you have these spin states, so up or down. Proton NMR, or proton is, or hydrogen is essentially 100% abundant. Carbon is only 1.1. So the gist of this is when you're looking at a signal, you have this unique set, right? So within that, there are these spins, but then the neighbors also have spins. So what happens is the signal you're looking at can sense the spins of the neighbors. And that influences the signal that you're looking at. But because carbon abundance is so low, it's very rare you're going to have two carbon-13 atoms right next to one another. Hydrogen is essentially 100%, so all of the hydrogens are NMR active. So the instrument sees them, the neighbors sense one another, and that's what you get these lines. The different lines are called splitting. So the reason you only see a single line in carbon spectra, really what you're seeing for that ketone, as I've shown with the up here in this area right here with the check mark, when you see a signal, you're basically seeing a carbon at that specific position. So within the bulk sample, you have 4 different molecules where that C13 label is shown by the red dot. Then in the spectrum below, I've just colored them in where those signals appear. So stated another way, because the abundance of C13 is so low, it would be very rare that you have one molecule that contains all of them. So those red dots would be the C13 label. So the fact that it's rare to have 2 C13 carbon atoms right next to one another, those spins do not talk to one another. So the carbon atom itself is just a single peak. Is that clear as mud? Any math majors in the crowd? So this is like a probability problem. Like for 4 carbons, what's the probability of having a molecule with all of those carbons as a C13 labeled? So it's going to be pretty small. So again, the NMR experiment, all of the hydrogen atoms are active, so the NMR sort of senses them through what's happening within the magnetic field and then the radio pulse hitting them. And we sort of already answered all of this because the student said it's the N+1 rule. So now we're gonna understand why is it N+1. So we had, again, 4 lines, 1 line, 3 lines. And the empirical observation from that is when you look at this signal, you can tell that its neighbor has 2 hydrogens. So 2 + 1 gets you 3. When you look at this one, it's a single line, so there's no neighbors. 4 lines, it's telling you there's 3 neighbors. And why is there's this +1? Well, it has to deal with the spin states. So the probabilities of those spin states being up or down, what are all the combinations you can get? And it turns out you look at the number of neighbors and you add 1, that accounts for all of the spin states. So here we said number of lines, A was 3, so that would eliminate choices C and D. B was 4, so that would eliminate A. B would be the correct answer because C is 1 line. And to further sort of explain some logic, I'm going to use this term attached hydrogens. So A is a CH3 group. C is a CH3 group. And then B is a CH2 group. So this spectrum alone, is it blows out of the water that you can't memorize. Like a CH3 group is always going to be a single line or 3 lines. A CH2 group is always going to be 4 lines. The number of lines is always determined by the neighbors. So let me write another thing in blue here. I'm just going to write it below the signal. So A we said was CH3. So its integration is 3 hydrogens. C was also CH3, so that's 3 hydrogens. The B was CH2, so that's 2 hydrogens. That's the integration. Or as we've just done from the uniqueness, we were calling it a ratio. So I just want everyone to be clear. When you're looking at a signal, the integration is the attached hydrogens. The number of lines is due to the neighboring hydrogens. So make sure that that's clear in your understanding. So the number of lines, we refer to those as specific names. So A has 3 lines. We call that a triplet. B has 4 lines. That's called a quartet. C has 1 line. That's called a singlet. So rather than saying, the signal with 3 lines, we just say the triplet at 1.05. So triplet, singlet, quartet. And then to state it explicitly, we can count that and say there's 3 unique signals. So that relates to the uniqueness. There's 3 unique sets. Questions? So when we were doing the uniqueness, we were really just doing a first approximation. You know, how many sets are there? At that first approximation, you can say, well, everything's a singlet. But then when you do the n+1 rule for the neighbors, you're doing a second approximation of how those single peaks will change based on the spin states of the neighbor. So again, that's the important thing for your second approximation. I would say the the learning skill here, say you're going into medicine and you need to do imaging. You need to look at enough images to say, okay, this arm bone, whatever it's called, when you take an x-ray, it looks normal. But then when it looks broken, what does it look like? So you need to have a basis of what is the normal case and then what's abnormal. So the uniqueness exercise is giving you mentally the idea of how many signals you should expect to see in the data. And then when you go through these other levels of analysis, now you're refining it more. So here's a table that helps us arise or conclude that it is the n+1 rule. And so what we're doing, let's look at signal A to start. We've said that that's a CH3 group. And it has the neighbor B, which is 2 hydrogens. And it's leading to the signal with 3 lines. And we do that same analysis. We look at signal B. It's a CH2 group. That's the integration part. It has the neighbor A with 3 attached hydrogens, and it gives 4 lines. Signal C is a CH3 group. There's no neighboring hydrogens, so no attached hydrogens. That gets you 1 line. So when you go through that, you'll ultimately conclude that it is the n+1 rule. That determines the splitting when you do your second approximation. Any questions? And this table summarizes everything that we've learned. So you look at the signal, what type is it, what are the neighbors, how many neighbors are there, you apply the n+1, that gets you the number of lines, and then you just convert that into the word. So 3 lines is a triplet, 4 is a quartet, 1 is a singlet. And so now we can summarize the number of neighbors. So this number is increasing. you apply the n+1 rule. That gets you the number of lines and then the name. So you have the signal name and then the abbreviation. So singlet, doublet, triplet, quartet. And then things get a little weird once you get past quartet. Because if you think about it, you know, what's the maximum number of neighbors you can have? And then, you know, what are the equivalency of those neighbors? So it gets a little bit complex beyond 3 neighbors. So there's the names. You know, you definitely want to remember, you know, singlet, doublet, triplet, quartet. And again, how you can back infer about the signal you're looking at. Any questions? So let's see if we can put this into practice. So propane, CH3, CH2, CH3 is the third hydrocarbon alkane homolog. Homolog just means series. We're going from methane, ethane, propane. How many unique signals do you expect to see in the 1H NMR? So 2 signals. And again, this is the uniqueness. So there's 2 carbons, 2 unique set of hydrogen. And then what is the ratio of those signals? So 6 to 2. So the methyl groups are the same. That's your 6, and then you have your methylene, that's the 2. So for the 2 unique signals, what do you expect the CH3 groups to look like? What? So those groups, they're equivalent. So their integration would be 6. How many neighbors do they have? 2. So 2 plus 1 is 3. So it's going to be a triplet. So the CH2 group, that's going to integrate to 2. That's its ratio. The 6 to 2, that's 2. How many neighbors does it have? So 6. So 6 plus 1 is your 7, so septet. So I'll tell you now, like, that's sort of like an ideal case. It's pretty rare that you would ever see like a septet in a more complex molecule. So here's what it looks like. Here's your propane. And so now based off that analysis, you know, we said the CH3 group should be a triplet. So the integration of that signal has to be 2, or has to be 6. The other signal is more downfield. I always confuse that amongst myself. When you look at it, it's hard to see 7 lines, right? So it's kind of small. So there's 7 lines, that integrates to 2. Notice the size of that triplet versus the septet. The reason those lines at 1 and 7, imagine you have a lot of area, so that's what the integration is. You're pulling that area further apart to accommodate those lines, and they sort of get lost in the baseline. So you see the line at 4 right here is the tallest, but 1 and 7 are really hard to see. And so that brings up another point which will be more addressed on Wednesday. So the triplet is 3 lines. Is there something else about those lines that we should be concerned about?
Is it like the range of the heats?
So the range is one thing. That means, you have the 3 lines, and those 3 lines are at different chemical shifts, right? That's how we can see that there are 3 different lines. What about the intensity? By intensity, I mean height. So if I were to draw a line, so I'm just going to number those 1, 2, and 3. So 1 and 3 are about the same height. If you had to approximate, what do you think the height of line 2 is? It's about double it. So the nature of the signal, like a singlet, it only has 1 height. A doublet has 2 lines. What do you think the height of those 2 lines are? They're the same. The triplet, the height difference is 1 to 2 to 1. And so there's another trend there that we have to account for that, again, is based on the spin state possibilities. So there's more information to infer from a proton NMR signal than a carbon NMR signal. So we have about 12, 11 minutes left. We'll do some practice, see if this is making sense or not. We have a molecular formula of C3H7Br, and the data is shown to you in tabular form, so you don't see the spectrum. What's the name of the structure? Said 2-bromopropane. Any challengers to that? Just accept it. So how are we going to accept that? So C3H7Br. Remember, for calculating degrees of unsaturation, halogens will add to the hydrogen count. So this becomes C3H8. You determine degrees of unsaturation for n equals 3. You'll find that it's C3H8. So this has no degrees of unsaturation. So no pi bonds, no rings. So we can propose 2 constitutional isomers. There's 3 carbons. For the first one, we just put the bromine at position 1. The second one, we put the bromine at position 2. So what is this right here telling you? There's 2 unique sets. So for 1 bromopropane, how many unique sets are there? 3. For 2 bromopropane, how many unique sets are there? 2. So that right there gives you the correct answer. But if you dig deeper into it, you can then make the assignments. I'll just call this signal A, signal B. Signal B is at 4.32, so that carbon must be bearing a heteroatom. 1.71 is going to be your A signal. And then we can look at the integration. So from 2 unique signals, it should have a ratio of 6:1. Notice now, see that this signal A, it says it's a doublet. So we're looking at the methyl groups. They integrate to 6. There's only 1 hydrogen there. So 1 plus 1 is 2. So that signal should look like a doublet. Questions? So C4H9Cl, how many degrees of unsaturation are present? So 0. This becomes C4H10. So when N equals 4, this is the alkane formula. So 0 degrees of unsaturation. So the same exercise. Now, where this gets a little different, remember when we got up to 4 carbons, you can have linear, and then you can start having branched isomers. So for that number of carbons, you're dealing with more constitutional isomers now. So we can say linear and branched. So how many do you think there are? So I'm going to put 4 by linear, and then branched I'm going to put 3. That just means the longest carbon chain. So if we want to draw all the linear constitutional isomers, we'll draw 4 carbons. And then what you're doing is just sticking that chlorine in there in a logical fashion. So we can put it at carbon 1, or we can put it at carbon 2. And that's it. So if we go down to the branched, the longest chain is 3. Now we have a carbon and a chlorine. The carbon has to go at position 2. And now we can stick the chlorine at position 1. Or we can put it at position 2. So this would get us 4 isomers. And hopefully you can see where this exercise is going now. You're going to be presented the data in different ways for each of them because they all have different uniqueness. And we're going to relate that back to the proton NMR. Any questions? Yep.
Can you not put it to the bronze carbon?
Like that. So what you have to be careful of, this is the same as that. So imagine, does this show up as a dot? Okay, so imagine if I put this dot right here, if I could rotate that, it would rotate right onto that. So that means it's the same thing. So the 4 constitutional isomers, which one has the following NMR data? So 1-chloro-2-methylpropane. So that tells us there's 3 unique signals. So I'll just say A, B, C. And those would be the assignments based on the integrations and the chemical shifts. So notice B, I put this word multiplet. A multiplet is something that is not well defined. That's typically, again, based on the instrument resolution. So why is it that described as that? So that H on that, what I'm saying, carbon B or whatever, it's 1H, but it has 6 neighbors of one type and then 2 neighbors of another type. So total, that's 8. So 8 plus 1, 9. When you get up into those large numbers like that, it gets a little bit complex in terms of interpreting it. And so again, this is a nice example that your neighboring hydrogens can be different types of hydrogens. So which constitutional isomer will have a single peak in the proton NMR? Two chloro, 2-methylpropane, so D. When you're on that carbon, you go out CH3, CH3, CH3. All of those are the same. So since they're the same, it's a single peak that would integrate to 9. So we're about out of time, but there's only like 2 or 3 more slides that you can go through. I'll give you a hint. There are the other 2 isomers. You just have to assign them based on how the questions are presenting the data to you. And then what we'll do on Wednesday is, and then look into the intensity of those signals. You know, why is a doublet have equal intensity among the two lines? Why is a triplet 1 to 2 to 1? And then what is a quartet?